let's have a quick look up here. I wanna just kind of go back and revisit for a second the antiderivative stuff we talked about at the beginning of chapter 4. And so, let me pause for 1 sec here. Okay, so if we make a statement like this, right? This we've come to know this as an indefinite integral. So we know the relationship here. We started off with this just being calculus jeopardy, right? We said that we had some function here, and our goal was to work backwards and find the function whose derivative is that, right? For example, we had something like the antiderivative of cosine x dx is what? Sine x plus c, right? Because the derivative of sine x is cosine x, right? Yeah. Okay. So then we could say in general that this is true then. We know that f of x is really just capital F prime of x. It's the derivative of the antiderivative, right? Yes. Okay. So then what if we have something like, this, a little different. We're going to extend this just a tiny bit. So that would also work, wouldn't it? Right? So the big F could be a composition of functions. It could have an outside function and an inside function, right? And in this case, all we're saying is that if we differentiate capital F of g of x, we're just going to get back this. So we've got an outside function of some inside function, and we know that when we differentiate compositions of functions, we have to use the chain rule. That's really all the chain rule is for, is differentiating layers of functions, right? So if we differentiate little f of hand, we're going to get back f prime of hand times g prime, right? Yeah. Okay, but more importantly, if we differentiate capital F of hand, we're going to get back capital F prime of hand. But isn't capital F prime the same as little f? Yeah. Right? See what I'm saying? So another way we could write this if we wanted to, we don't need to, but we could also write this as the antiderivative of capital F prime of g of x times g prime of x dx, right? Mm-hmm. Okay. This is when this kind of, here's a situation where this would come in handy. What if we had, for example, see if you can tell me the answer to this one. What if we had the antiderivative of, okay, how about, let's do right there. Make this really simple. Yeah, can anybody tell me what that answer is going to be?
Is it going to be x squared times x squared plus 1, and then...
Okay, what do you suppose that 2x is there for? Why is that significant? Okay, that's the derivative of the inside function here, right? Yeah.
Yeah.
So the outside function is really just hand to the 1, isn't it?
Yeah.
And the inside function is just x squared plus 1, right?
Yeah.
So what's going to be, this is the derivative of what then? X squared plus 1 squared, right?
Yeah.
Over 2. Yeah. Whoops. Okay. Plus c, right? Let's just check it out. See if that works. Okay. So if we differentiate this, the constant goes away. And what do we get here? Well, we're going to get the derivative of hand squared is 2 times hand to the 1. So the 2's cancel, right?
Yeah.
And then when we differentiate hand, we get 2x, right? So it works. Okay? But there must be an easier way to do this than having to recognize that every time. Well, there is kind of a shortcut way of dealing with this. If we go back to our, let's go back to our general expression here. If we have the antiderivative of f of g of x times g prime of x, let's leave that dx, equals f of g of x plus c, we're going to make a change of variable here to make this look simple. This is called, and the technique that I'm showing you today is called, the most common name for this is called u substitution. really, it's just a variable substitution, but we always choose the variable u. So let's make the substitution. Let's let u equal g of x. Okay. So if u equals g of x, then what is du equal to? Yeah, it'd be g of x dx. And how come? Because the intermediate step, if you want to think of it this way, is if I took the derivative of each side with respect to x, then wouldn't I just get du dx equals g prime of x? Mm-hmm. Right? But if we write those in differential form, this is really just equal to, if I multiply each side through by dx, or I could even just jump from here to here if I just differentiate using differential form, right? Either way you want to look at it, you end up here. Well, look what this becomes then. This whole integral up here could be written more compactly as the integral of f, and you gotta say this carefully, f of u, right? That's f, but that's a u, right? And then this whole thing right here is just du, right? And what's that equal to? It's equal to capital F of u plus c. Okay? Did I do anything there that's that's so profound? Not really, because if we could have started here, and if I had asked you this question, what is the antiderivative of f of x dx? Well, you already told me the answer. You told me the answer is capital F of x plus c, right?
Right.
So what's different between this expression up here and this one right here?
Not much.
The only difference is we wrote a u instead of an x, but the relationship is the same, right? Okay, so then our goal is, when we see problems like this, we want to ask ourselves, can we make a u substitution that's going to make this composition of functions look like a simple function? Okay, so let's just redo this one that we did up here using a u substitution. Okay, so what would my, how about if I just grab this? Okay, so pretend we don't have the answer yet. What's our u substitution going to be here? And our goal is, when we pick a u, we want to pick a u so that u and du So where do you, and this is where calculus starts to become more like an art, and a little bit less like just math. Because there is some technique involved here. I mean, you have to kind of think, as these integrands get more and more complicated, there's lots of different possible choices for your U substitution, and you want to pick the best candidate. They won't always work. Yeah, exactly. But typically what you want to do is you want to pick the hand. What we've always called hand is now going to be called U. So the argument of the function. So here we've got this function, that we've got this quantity to the 1 power. Well, whatever's inside that, what we call hand, is a good possible choice for U. Okay? It may not work. If it doesn't work, there are some more advanced techniques that we won't get to this year that you'll get to next year, where something that perhaps will work. And we've even got a couple tricks up our sleeve for this year where we can still make it work, even if it doesn't seem like it's going to. Okay? So our choice here would be, let's let U equal x squared plus 1. Well, if U equals x squared plus 1, what's du?
X squared plus 1.
It's going to be 2x dx, right? We're just differentiating now, not with respect to anything, we're just differentiating, right? So by the chain rule, the derivative of 1 is 0, right? But the derivative of something squared is 2 something times the derivative of what's inside. It's just a dx. Okay? So look what we get then. This part right here becomes a u, and that part becomes a du. And so we can make the substitution then. Let's trade this complicated looking integral for an easy one. It's just u du. Well, what's the answer to that one? That's easy.
U to the second
Okay.
power
Over 2
Wait,
plus
how
c,
do
right?
you know that?
Well, because this is just a pattern. If I asked you what's the derivative of x dx, you would have told me x squared over 2 plus c, right? Because it's the power rule for antiderivatives. Same thing, only this is a u instead of an x, just a variable, right? So by our rules, this is equal to u squared over 2 plus c. Well, what's left for us to do then?
Nothing.
Well, we got to reverse the substitution, right? So now we've got to say, okay, we made this convenient by making a u substitution. We got our answer. Now we'll just shift back. We'll reverse the substitution and plug the x's back in, and we're done, right? So the last step would be, okay, what was our u? Well, our u was u equals x squared plus 1, so our answer is going to be the quantity x squared plus 1 squared over 2 plus c.
Okay.
Okay, see how that works?
Yeah, so it's just making your life easier.
Yeah.
By doing
Yeah. Okay, let's try another one.
You want some more?
Okay, how about this guy? Okay. That one doesn't look like one of our standard forms, does it? We know how to take the derivative of cosine of x, or cosine of u, but we don't know how to take the derivative of cosine of 5x. So what's our u substitution? 5x, right? We're going to let u equal 5x. So if u equals 5x,
But du could equal 5 though.
well no, u is just 5x.
But we have
So then we can, now we need to know whenever we define a u, we have to know what its derivative is also. So the very next step is always, what's du? 5 dx, right? Okay. So now can we make our substitution? Well, yeah, we can, because look, this is, here's our u, right? And here's our du. It's sort of split up, but who cares, right? Multiplication is associative and commutative. We don't have to multiply things in order. 5 times dx in any order is still du, right?
Yeah.
So this whole thing then just becomes the integral of cosine of u du, right? What's the antiderivative of cosine u du? Sine u. cosine u
Let's see.
plus c. So all we have to do then is just reverse our substitution. Well, what's u? 5x. So what's our answer?
Sine 5x.
Done. Okay.
So, do you treat du as a constant then?
No, du is not a constant, but du, remember that this fits the form, we call this the integrand, this is the integral sign, and this is just the variable of integration, right? So this fits our rule. We're just playing calculus Jeopardy when it's written like this, okay? And really, now that we know what differential notation looks like, we can see that in actuality, this whole thing is really what we're playing calculus Jeopardy with, because what we're really saying is the derivative of what is cosine u du? Well, sine u in differential form. But you don't have to even think of it that way. You can just think of it as good old-fashioned calculus Jeopardy, right? Where this is just the variable that we're using, and this is the function that we're trying to undifferentiate, right? Or anti-differentiate. Funny you should ask.
Look at this, people smile.
Okay, so let's try. Okay, let's try one like this. Okay, what are our options with this one, by the way?
Just go home now.
No, we actually, you guys could have done this one yesterday, but it wouldn't have been very fun. What would you have to do first?
Too much.
Yeah, we have to expand it all out and make a polynomial out of it, and then integrate term by term, right?
Well, let's just put it in our calculator.
No, let's not.
Have someone else put it in
Our-
your calculator.
Our calculators aren't really going to help us here, though, because the TI-84s, at least, they're not going to take a derivative symbolically. Now, the TI-89s will, or the TI-Inspires will. They'll actually tell you what in terms of variables, what the answer is. But the TI-84s will not, okay? Right, exactly. Okay, so we don't want to do this, though. We could FOIL out x squared plus 1 squared, distribute the x, and integrate. But let's see if we can pick a u substitution instead.
And
Okay, so what's our u going to be?
X squared plus 1.
X squared plus 1, okay? So if that's the case, then what's du?
2x dx.
Okay, so now let's see how much we can account for in our problem. So we've got a u squared, but then look what's left over. What's left over is an x dx, not a 2x dx. So what can we do? I know that this is the part that's actually represented in my problem. So if I want to isolate that part for substitution, what do I have to do to both sides? Divide by 2, yeah. So all I've got to do then is just say, well, x dx equals 1/2 du, right? And now I make my substitution. So what do I get? Then I just get the integral of u squared times x dx is a 1/2 du, right? So why did I put the 1/2 out front? Why not? Because that's where ultimately we want to put it anyway.
Where did it come from?
It came
Oh,
from
from
here, right? So here's what I did. Here, let me go back just a little bit.
Thought you just wanted to.
So this right here
English, we ate lunch in there.
becomes that, right? Okay. X dx becomes 1/2 du, right? So this stuff becomes that stuff, right?
I still don't understand where the 1/2 came from.
Well, the 1/2 comes from here because du equals 2x dx, but I don't have a 2x dx. I only have an x dx.
Wait, why did you put the answer?
So say it again.
Is that just another way to write the answer?
Yeah.
Yeah, this isn't as good a way. We're going to have to we would wanna simplify this and take the constant out front. Okay? Does that make sense?
Yeah.
And we can do that, we wanna get as much out of the integrand as we can. Well,
That's not our
this
answer.
isn't really our answer anyway. Okay. Does everybody see where this 1/2 du came from then?
Yeah.
Right? So then all we would do here is pull the 1/2 out front. And what are we left with? Well, the antiderivative of u squared du, that's an easy one. What is that?
Yeah.
U cubed over 3. So I just end up with then u cubed over 3 times 1/2. I could, if I want to, I could just make that 1/6 times u cubed plus c. Last step,
So put it back in.
reverse the substitution. So we get,
So the 1/2 comes from 1/6 times 3. I mean 1/6 comes from.
yeah, from 1/2 times 1/3.
Okay.
Yeah. Right? Because that's just u cubed over 3. Well, 1/2 times u cubed over 3 is the same as that. Or I could put the 6 on the
Can we
bottom.
double check our answer by finding the derivative of that?
And we could.
Well, it's not.
But we could. It would work. Okay?
This seems so.
Let's try another one.
Whoa, no,
Leave it there for a sec.
Leave it there for
I'd rather do a puzzle.
Wait, but I don't know get how you found it. Okay. I'm not confused if we find the derivative of 1/6. That doesn't equal x squared plus 1/3.
Yeah, it does. Watch, if I differentiate this, I'm going to get hand cubed. Derivative of hand cubed is 3 times hand squared. So that's going to give me 1/2 times x squared plus 1 squared times the derivative of what's inside is 2x. So the 1/2 and the 2 can't. See what I'm saying? So it would work. It would work. Okay? We ready? Can I turn it? Okay, try this.
Alone? Yeah, no, I don't know.
Okay, what's my u this time?
2x plus 1.
2x plus 1. So u equals 2x plus 1. Then what's du going to be? 2 dx? No. 2 dx? Okay, but we don't have a 2 dx.
So do you even need the g? But yes, you do, because you have to divide by 2.
Okay?
But square root of 1/2 du.
Hang on.
Plus dx.
Okay, is everybody with me so far?
Yeah.
Okay, watch this closely, because this is what you should write. What I'm doing up here now is what you should write when you do these problems. I did.
Okay.
So then we got to account for what we have. Okay, so then this looks like, this might help. So this looks like now the integral of the square root of u, but look what's left over then. I just have a dx. I don't have a 2 dx, right? So what I've got to do then is I've got to make my substitution for that, right?
Yeah.
That's okay. All I have to do is go down to this equation and say, this is just an equation that relates dx to du, right?
Yeah.
So write dx in terms of du, just divide each side by 2,
Yeah.
right? So I get du over 2 equals dx, and there's my substitution, right?
But
So
do we
now-
have to put a 1/2 in front?
Yeah, then we'll just put the 1/2 in front. So then now what do we have? This just becomes the integral of u to the 1/2, really, doesn't it?
Yeah.
Right? Times dx is just a 1/2 du. Okay. What did we accomplish there? Does the integral look, is it really that much different? Not really, because what we had here was some function to the 1/2, right?
Yeah.
Integral of some function to the 1/2. What we have here is the integral of some function to the 1/2. But the key difference is this is an integral that we can do. This matches our table of standard forms, right? This just fits the power rule, right?
Yep.
So what is the answer to this then? This one then? What is the antiderivative of u to the 1/2? So u to the 3/2 divided by 3/2, which we never do, so instead we multiply by 2/3. So we get, there's our 1/2 times 2/3 u to the 3/2 plus c, right? And the 2's will cancel. Which one? This one? From red to red. Well, this is actually doing the antiderivative. Okay. And that's our goal, right? Our goal is to take the integral, we say. But we can't take the integral until we've written it in a way that we know how to do it. Okay? So all this u substitution is doing for us is it's allowing us to take an integrand that doesn't look like we can deal with it and allows us to deal with it. Puts it in a form that allows us to integrate. Okay?
So do we do the plus the after the answer too?
Always, yeah. Because the constant's still going to be there. Okay, but then last step would then just be, okay, now our u's helped us out, we got an answer, now we just reverse the substitution. So we get 1/3 times u is actually 2x plus 1 to the 3/2 plus c. And we're done. Yeah. It's, I mean, this not only is it so much easier, it's the only way to do it. Okay, try one more. How about this? What if we've got okay, suggestions. What's our u?
3x.
3x. Okay, let's try u equals 3x. So what's du then?
Wait, 3.
3dx.
DS.
Okay, so applying those substitutions, we get the integral of sine squared u.
What do you do if it's like 2x inside the sine squared and maybe like just x inside the cosine squared or the cosine?
That'd be much more difficult.
Would we get something like that?
No, I won't. Just because there's so much trig going on with that. That's really the tricky part. So we get a sine squared u times a cosine u. But now look, we don't have. So that accounts for this and this. This is what's left over. So what is dx equal to in terms of du?
1/3 the.
Okay, so 1/3 du. Now I'm going to rewrite this because that is still not a form that we know how to deal with, right? So let's rewrite this just slightly. Let's rewrite this as 1/3 times sine squared u is really sine u quantity squared, right?
Yeah.
So maybe we need another substitution. Let's make a v substitution. Yeah, we can do that. So what might be a logical choice for our second substitution?
Sine.
Okay, sine u equals v, right? So if we let v equal sine u, what's dv?
Sine.
Cosine
DV.
u du, right?
What? Oh yeah.
Right? Okay, now that fits really well,
Yeah, because we have it.
right? So then this gives us 1/3 times the integral of v squared dv, right? Okay, at last, that's one we can do, right? Okay, so what's the answer to that one?
Now, V cubed over 3.
V cubed over 3 times 1/3, so v cubed over 9 plus c, right? Or, I mean, I could do it as 1/9 times v cubed. Let's do that. Right? Yep. Okay, we're okay with that, right? That's just power rule. From here, because ignore the 1/3. The antiderivative of v squared is v cubed over 3, right? Times 1/3 is 1/9.
Wow.
Okay? Make sense? Right?
Now we gotta make two symbols.
So it would have been this.
1/3 times 1/3.
Does that help?
So you'd get
Okay, so now we just have to, we're done with the calculus. Now we just have to reverse the substitutions. Yes, sir.
Isn't dv negative cosine?
Derivative of sine is positive cosine. Derivative of cosine is negative sine.
so the answer is sine 3x.
Okay, but now we gotta work, we made two substitutions, so we gotta work our way back through both of those. We gotta undo them in order, right? So we said v was sine u. So first we get 1/9 sine u cubed plus c. And then finally, if we work our way all the way back, u equals 3x. So we get, 1/9 sine 3x. We'll just say sine cubed of 3x. Okay? We're done. Okay, so now, could we have, here's my question, in hindsight, and I'm not suggesting you have to do this. Sometimes it's easier to take multiple substitutions that are small, but could we have made one big U substitution that would have done both of those things?
Yes.
Okay,
Yes.
so let's try it.
You could sine
Maybe cosine 3x.
Could we have done one big U substitution?
All of it.
Keeping in mind, here, let me do this one little thing. This might help. If we rewrite it like, how about like this?
Maybe just
That
sine
whole thing.
3x.
How about sine 3x? Okay, so we could let U equal
We should probably rewrite this one again.
sine, yeah, I think it's a good idea. So we could write U as sine 3x. Now by the chain rule, what's du? Derivative of sine hand is
And
cosine hand times the derivative of hand, 3 dx, right? And so then look what we would have. So we would have an integral of u squared, but then look what's left over. We'd only have a cosine 3x dx, which is the same thing as 1/3 du, right? Okay? Exactly. And then that gets us to the very same integral we took a second time, right? So this is going to be 1/9 u cubed plus c, but now there's only one substitution to reverse. So that gives us 1/9 times sine 3x cubed.
Wow.
Okay?
why wouldn't you substitute?
Well, I mean, that's kind of a big substitution. You can do it that way. As you get better at it, you'll definitely probably do it that way.
We're already put.
But I want you to see that you can just break it into, I mean, you might have 4 substitutions, possible. Something like that.
No.
Can you always break it down into one like that?
No, it doesn't always work. But when it does work, it's a good technique. Okay, so what about, okay, I want to find an example where we have to complete. Yeah, how about this one?
I'm waiting for this loud.
Okay, what about that? Now, I want you to make this connection here too. You see that if there's a red flag in this problem, where is it? Below the square root. Yeah. Because if this were a different kind of problem, like if I had given you one like this instead, what if I had said the antiderivative of like x plus 2 times the square root of x dx? Well, that's not, we can do that.
Yeah.
Without anything fancy, I could just distribute the square root and get I could just get x times the square root of x is x to the 3/2 plus 2x to the 1/2 dx, and just do it in two separate parts. That would have been easy. We could have done that one easily, right? This is different though. This is different though because inside the square root is where I've got the x plus 2. So you see that I can't distribute, I can distribute here, but I can't distribute this x over that square root. You get it?
Get it.
So this is hard, this is easy. Okay? Well, maybe we can still deal with this though. What's probably, based on what we talked about today, what's our best option?
X plus 2.
Yeah, what if we could try to make this one look like the red one that I just erased? Let's let u equal x plus 2, and so then, worst case scenario, we're ending up with a square root of one thing. Square root of a variable, which I can distribute if necessary, right?
Right.
Okay, so we end up then with, if we let u equal x plus 2, what's du equal to?
X dx.
No, just dx, right? Okay, so then what do we get? We get the integral of the square root of u times du, but look what happened. It's an incomplete substitution. There's still an x in there. Now, our substitution has to be complete before we can do this thing, right? You can't mix x's and u's. But there is a way out of this. What could I do there to complete the substitution?
Times du by divide by.
I almost made it. I stalled out though. I got most of this converted to u's, but this one little piece here was left behind. Is there a way I could convert that x into an expression in u?
Yeah. U over 2.
Ah.
There's an equation that relates x and u, right?
Yeah.
So if I ever want to think about what you've done all through your lives in algebra, when you want to substitute for a variable, you isolate it and substitute, right?
Yeah.
Same thing here. So let's isolate x and substitute. Now, this one works because we're able to write x as a function of u completely. That won't always happen. There might be instances where the relationship is complicated and I can't solve for x in terms of u, and then this method falls down and I can't do it.
So.
Okay. But in this case it does. I could complete this substitution. I could say x equals u minus 2, right? And so then I can plug that in for x and save the day. So now I get the integral of the quantity u minus 2 times u to the 1/2 du. Yeah, I still have to do some calculus, but now it's doable calculus. If I distribute the u to the 1/2, I get the integral of u to the 3/2 minus 2u to the 1/2 du. Okay, well, what's the answer to the first one?
Yeah, maybe we'll take a break. Wait, how does that equal 4/2?
Because it's u to the 1 if I distribute, is all I'm doing. U to the 1/2 times u to the 1.
So
Is u to
1
the-
like plus 1/2.
Yep. Okay, so it's this one's going to give us u to the 5/2 over 5/2, which is the same as times 2/5, right? Minus 2 times u to the integral of u to the 1/2. What's that? U to the what power? 3/2. 1/2 plus 1, right? So that's going to give me minus, minus 2.
times 2.
Okay, but I'm going to get minus 2 times just this part gives me. Yeah, the two just stays there, right? Really, what have we done here? I've skipped some steps, but all we've really done is, listen closely. All we've really done here is we've just broken this up into two completely separate integrals, but we just didn't bother writing it all out. Okay, so we got this one by itself and then this one by itself. Okay, that's what we mean by integrating term by term. So then I get 2 times, this is going to just be, what, 2/3 u to the 3/2 plus c. And so then we just get, now if we reverse the substitution, no, because we're taking antiderivative, right? playing calculus Jeopardy. So now u equals x plus 2. So if we reverse that, we get 2/5 times x plus 2 to the 5/2 minus 2 times 2/3 is 4/3. X plus 2 to the 3/2 plus c. We got it. Good enough for one day? Looks a little better. It's good. Okay, so all we have left to do is just apply this to definite integration, and then I think that's probably about all we're gonna do.
For the whole year?
I think so. That's all we'll test over.
Can we have work days?
So you can have some work days, yeah.
For the rest of the way?